We'll be talking about the definite integral today. And again, it's going to be another longer lesson I would normally spend 2 days on, but I'm just going to put it all in one video. And if you want to spend 2 days going through it, I think that would be a smart move on your part. Okay. So the definite integral. Okay, let's talk about the definition because I haven't seen this definite integral word before. It says if f is a function defined for x between a and b, we divide the interval, the closed interval ab, into n subintervals of equal width, delta x, which can be defined as b minus a over n. And we let a be one endpoint and b be the other endpoint of these subintervals, and we can do sample endpoints. Don't get caught up with all this notation stuff. I want you to know that everything's going to be very similar to what we did last week. All right. And so the definite integral from a to b is going to look like this. Say the definite integral from a to b, and it's going to be as a function, and that is dx. And the good news is that this is going to look very familiar to what we did on the last video, where we took the limit as n approaches infinity of the sum. My sums are looking rough. I apologize for that. The sum as I goes from 1 to n of f of x sub I times delta x. If I'm going to actually use this, I would have to put a star right there for f of x sub I. I mean, don't worry about that star. I'm not going to get into that without you guys being here. So, these are the same. So, I just want to point out a couple things to you. And is that all of this right here, this limit of the sums right here, is I'm going to be able to just write it as an integral. Okay? And that's exactly what this is. Okay? This is called an integral sign. That's an integral sign. Okay? And all it is an elongated s. It's an s that has been pulled on top and bottom to make it look longer. And the s stands for sum. All right? The same sum that we're doing back here. But this is just going to be reserved for whenever I do the limit as n approaches infinity of this sum. So you won't necessarily have a set number of rectangles to find on this. Otherwise, this is very similar to what we did with the area problem last week. Right? Now, whatever this function is, you will hear me call it the integrand. Or I'll just say the function I'm taking the integral of, but more specifically, it's known as the integrand. And look what happened to my delta x from the last video. My delta x, it was so small, it just simply became a dx, which means a difference in x. And that is the same dx that we used when we did dy over dx. Okay, it just means x is just a little bit off, right? Which is going to be the width of my rectangles. Now, whenever we work problems this way, and we're working to find this sum, notice this one does not have a limit. So n is not going to infinity. So like the other day, we did n equals 4, and we put 4 approximating rectangles underneath a curve. Whenever I do that, I'm going to be referring to this as a Riemann sum. So I'll have a set number of rectangles underneath the curve. All right, it might be 4, it could be 8, it could be 3, it could be 5. We're going to play with that over the course of this video. Okay, but let's just talk about the notation first. All right. Oh, we have a theorem real quick. All right, it says if f is integrable. So if I'm able to integrate it on AB, then the integral from a to b of f of x dx is simply equal to the limit as n approaches infinity of the sum as I goes from 1 to n of my f of x sub I delta x. All we're doing the same problems. We just have to rewrite it like this. And here's the formulas. I don't know how many pictures I'm going to draw today. I might just go straight to the formulas. But those are the formulas that we talked about, that we came up with when we were doing the area problem on the last video. So have those handy in the top margin of your notes, your homework, whatever you're going to be using to help you with your assessments. So now I want to talk about the notation. Okay. So I was given this. This is what I could definitely go through and draw a curve for this, but I'm wanting to write it in something called integral notation. Okay, so here's what we need to know about it. Okay, whenever I have the limit of the sums right here, it has to be the limit as n approaches infinity, and the sum as I goes from 1 to n. So I can't have a number in there. So as long as n is going to infinity right there, what I can do is I can just replace that with an elongated s. Now, we use this so much, they got rid of all this I notation that they have right here. And what I do is I simply just bring it over without the i's. We just have a very general function for it, instead of having all the i's in the way. Okay? Next thing to note is this delta x. Like I stated earlier, that delta x becomes a dx. Now, we'll be able to find this, hopefully, before we get out of Calc 1, all right? But in this case, we have a very specific integral that is on the interval from 0 to pi. And so what I do is I throw my 0 down here and my pi at the top. This is called my lower limit of integration. And this pi up here is my upper limit of integration. Right? My upper limit of integration. So sometimes we have those numbers, and sometimes we have something called an indefinite integral where we don't have those numbers. We'll be able to work with both, hopefully, over the next couple of weeks. Now, something I did introduce, I'm not sure how much we needed on the last homework, but something that I did introduce last time was the idea of these sums. These are the 3 basic sums that we will be working with these types of problems. Okay, so I'm just going to go over this one more time. If I'm taking the sum as I goes from 1 to n, okay, what that means is just 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus da da da, all the way up to 7, 8, 9. N is going to be infinity, so it just goes on forever. What I can do is, or suppose I just go to 6. What I can do is I can just bring this top n down, add 1 to it, so I get 6 times 7 over 2. So if I was wondering what all the numbers from 1 to 6 added up to be, I could just do 6 times 7 divided by 2. 42 divided by 2, 21. It's a lot quicker to do that than 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up. Okay, so it is a little shortcut for us. Okay. In the same way, if I was to throw a squared on all these, 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, my formula gets a little bit hairier. I get n. Here's the one that we used in that last video. Times n plus 1 times 2n plus 1 over 6. And a lot of you are saying, why? Where in the world does that come from? That is something above what we can do right now. But I'll be glad to show you during the Q&A if you're wondering where that comes from. It's something called mathematical induction. Okay? Now, if I change all those 2's up there and I do 1 cubed plus 2 cubed plus 3 cubed all the way up to 6 cubed, then I get this formula. I in no way expect you to memorize these formulas. We have, like I said, we have not dealt with these enough. So these will be on the board. You can put these in the notes. You're on top of your homework and have those handy to pull down. Okay? But we will be using them. Now, just brushing up on a couple of other properties from Algebra 2. When we did our sums, we always said that the sum of C n times, well, that's just C times n. Okay. Let me talk to you about that real quick. The sum of C. So what that means is, as I'm going to add C to itself, C plus C plus C plus C plus C, an n number of times. Well, if I add C to itself an n number of times, That's my definition of multiplication, c times n. And so that's where that comes from. So keep that in mind. We're going to be using some of these because we are going to get into some pretty long problems here in just a minute. Okay, now, if I have a constant that's worked its way in there, and I'm going to illustrate this in an example, that constant, if it has an a sub I behind it or something that has to do with I can move that constant out in front. Just like I did with the limit. We always did that with limits. It works for sums as well. So a lot of these are the same as limits as they are for these sums. So if I have the sum of A plus B, I can do the sum of A plus the sum of B. So a lot of people say, oh, well, it just distributes through. Well, I'm not really multiplying it, but it does look like it distributes through. It does go to each element. And so I don't think it's going to be too far of a stretch to realize that if I have a minus sign in there, obviously it is going to be subtraction as well. So it works with subtraction as well. We're going to need all that. Okay? So have that handy as well. I think whenever I work this in the example, all of this will make sense. Okay? So I want to go back to one of our examples. Might not use all those formulas here, but we will before the end of the video. I'm wanting to do a Riemann sum. Now, first of all, whenever I see that I'm doing a Riemann sum, it means I'm going to have a set number of n. And I luck out on this one because n's not going to infinity. All right? N's going to be, it says down here, 6. And so my function is x cubed minus 6x. I'm taking right endpoints, and I have from 0 to 3 is all I'm doing as my interval. Okay? So if n equals 6, so I'm just going to kind of get everything that I need on this. Oh, looks like I'm going to do it again here in a minute. So I'm just going to do part A real quick. And so if I have n equals 6, first up I'm going to find my delta x. My delta x is going to be b minus a, which is 3 minus 0 over my n, which is 6. So you're probably going to get nice delta x's like 1/2. You might get a 1/4 or a 1 or a 2. It turned out to be nice. Now I'm wanting to take endpoints. I'm wanting to take sample endpoints to be right endpoints. So you have to imagine divvying up from 0 to 3 all of these numbers, and I've got to have 6. Oops, 0.5. I have to have 6 endpoints on this. Okay? So imagine drawing our little rectangles up on all of these points, because remember, these are endpoints, and I have 6 rectangles on it. Looks kind of rough. 1, 2, 3, 4, 5, 6. I have 6. If I'm doing all the right endpoints, it means that I want the right 6 numbers on this curve. And so I'm going to omit the 0 for now. That doesn't make sense to you. I have questions ready on that. That's kind of weird to explain on a video. Okay? So that means that this guy is going to be my x1, my x2, my x3, my x4, my x5, my x6. So if I'm going to do a Riemann sum on this, I'm going to do the right 6. I'm just going to do the sum as I goes from 1 to 6 of the height of each rectangle times its width. Notice I don't have a limit in there yet, so this is very algebraic what I'm getting ready to do. I don't have the limit in there yet because I have a set number of rectangles. I only have 6. And so I'm going to go ahead and pull this 1/2 out in front. I know that my delta x is going to be 1/2. And so I'm going to skip down a step down here, and I'm going to pull that 1/2 out in front like I talked about in the other video. And so that way, I just need to plug in 1 in for my I. So that's going to give me, if I plug in a 1 right there, that's going to be my 0.5. I'm going to do this in several steps so you can kind of follow along. I'm going to plug in every number from 1 to 6 right here, f of 2. Well, f of x2, that's going to be f of 1. So it ends up, I'm going to take f of every number that I pointed out earlier, f of 2.5 plus f of 3. Okay? And you can imagine if I was to distribute this 1/2 through right here, I'm just doing length times width of all these rectangles that are coming up. Do I have 6? 1, 2, 3, 4. Good. So now, I just have to plug this back in to my function. I'm going to plug it back in for these two x's right here. And that's going to tell me the height. Actually, I pointed at B right there. Please forgive me. It's still going to work the same. But I'm going to plug it in for these x's right here. And so whenever I plug in 0.5 in for those x's, this is where I miss you guys, because you guys are so good at pointing this out. Negative 2.875. Okay. Whenever I plug in 1 up here for these x's, I just get negative 5. So plus a negative 5. When I plug in 1.5, I get negative 5.625. So I'm just going through and plugging in all my x's. Whenever I plug in 2, I got a negative 4. When I plug in 2.5, I got 0.625. And then finally, whenever I plugged in 3, I got 9. So what I want to do now, to find out what this Riemann sum is going to be, I just want to add together all these numbers and then multiply it by 1/2. And whenever I did that, I got my Riemann sum to be negative 3.9375. And that would be my answer for part A. Now, one of my first questions, if I was you guys, is how in the world did he get a negative right there? Let me show you what this curve's actually doing from 0 to 3. If I was to go back and draw this from 0 to 3, I get a curve that looks something like this. This is about 3 right here. So whenever I draw all of my approximating rectangles on here, some of them, let's see, I think there's supposed to be 4 that's facing down. Let me do that over again. There's going to be 4 of them that are facing down. These first 4. And then starting over here, they start going positive. And I get that just from all of these values that I had right here. All right? And so these 4 that are facing down, they all take on a negative value. So any area that's going to be below my x-axis on this is going to take on a negative value, while anything that's above the x-axis takes on a positive value. And so if I was to draw this accurately, the area that is underneath the curve right here takes on much more area than this small area right here that is above the curve. And so that's why this came out to be negative. It's because more area is down here below the axis than it is above the curve. So that's something new in math. We have a negative area because we are on the xy plane with this. So I want to show you the similarities between what we just found and if I was to change this now to an integral. So what we just did, we did this area formula, something very similar to this last week, or yeah, I guess last week on the video. I am going to turn on my eraser. And I'm actually going to evaluate this definite integral now. Okay? So whenever I evaluate this definite integral, remember, what this means right here is that I'm going to take the limit as n approaches infinity of the sum as I goes from 1 to n. So this time, instead of just having 6 rectangles, it's moving up to the infinite number of rectangles. And it's going to work just like we did last time. Okay? So first up, I'm going to need to find my delta x. My delta x is still b minus a over n, but remember, this time my n is infinity, so I really can't plug anything in right there. It's going to be small. I expect that because I'm going to have an infinite number of rectangles between 0 and 3 on this. So I'm just going to start at 0 right here. My first endpoint is going to be at whatever a is. And then my x sub 1, my next endpoint is going to be at whatever a is plus delta x. Well, my x2 is going to be at whatever this guy is plus another delta x. So I'm adding 2 delta x's to it. So I'm just adding a delta x to get to the next one. I'm adding 3 over n each time. All the way until I get down, I again want to find this ith subinterval. And as you can see, to work this, I'm just taking whatever this I is, and I'm multiplying it by 3. Whatever that little subscript is, I'm multiplying it by 3, and then throwing it over n. This guy right here is very important. So I just kind of did a pattern thing until I realized what it was going to be. In this case, 3i over n. So now I'm able to rewrite this as the limit of sums. Remember, I'm going to do f of x sub I times delta x, which in this case will be the limit as n approaches infinity, again, of the sum as I goes from 1 to n. Let's make it good with this problem. So f of x sub I is going to be 3i over n. I just pulled this guy over, times delta x. I knew delta x was 3 over n. And now I just have to use algebra and a little bit of calculus at the end to solve this all the way down, okay? So my first order of business whenever I work something like this is anything that doesn't have to do with this I right here, I'm going to pull it in front of the sum. That's going to help me out a lot because that sum is going to be the booger of this problem to work with. Sum as I goes from 1 to n of the function. So if I was to plug in this 3i over n into my function, I got to plug it in both spots. So I've got the sum of 3i over n cubed, just plugging it in for x, minus 6 times 3i over n. Okay, let's do some cleaning up here. So I've got the limit. I'm going to get rid of my subscripts for just a minute. That's 3 over n. I'll bring them back later. And then the sum, let's see, 3i squared, that is going to be 27i cubed over n cubed. And then 6 times 3i over n is just going to be 18i over n. Just did some multiplication on that step. Next up, I'm going to try to change colors in case you have questions on this later. Next up, I'm going to distribute this sum to each one of these terms, thanks to my sum property that we put on the board earlier. Okay, remember how the limit distributes to each one. The sum is going to do the same thing. So I am going to have the sum of 27i cubed over n cubed minus the sum of 18i over n. Have one more step that I want to show on this before I start getting somewhere, is that, remember I said I could pull anything out in front of the sum that doesn't have to do with I. So here's the trick on this, is that I want to make it so that the only thing that is behind the sum is either I squared, or in this case, I cubed. So this 18 over n, it doesn't have anything to do with this sum. because it's the sum as I goes from 1 to n. So I've made it so that my sum matches up. I'm going to be able to plug in exactly what we wrote down for the formulas here and here. Okay, now we're going to start progressing somewhere. This is where I wish you guys were here because I need to take this to the sideboard, but we'll get there. All right. So now I've got the limit 3 over n times 27 over n. Ooh, I'm going to be short on space. 27 over n cubed, I'm sorry. And then I'm going to plug in what I said the sum as I goes from 1 to n of I cubed was equal to. So that's n squared, n plus 1 squared over 4. Okay. Minus, switch colors here, 18 over n. And then the sum of I was just n times n plus 1 all over 2. Hey, good news on that step. We don't have any more of those sums floating around. We just have this horrible, nasty limit. Okay? And so from here, there's several ways that we can clean this up. All right? You can distribute the 3 over n through. I'm not going to do that just yet. I'm going to try to do this in as many steps as I can so you can follow it. What I'm going to do is I'm going to cancel both of these ends with 3 of these down here. Okay? So that gives me 27 times n plus 1 squared over 4n. Okay, that'll turn out nice. I'm going to do the same thing here. I'm going to cancel these n's that are out in front. So I have 18 times n plus 1 over 2. So that helped a little bit and got rid of some messiness. I'm going to expand my binomial and get rid of my inside parentheses on this next step. So if I expand that binomial, I'm going to get 27n squared, let's see, plus 2n, so it'll be plus 54n. So I'm expanding and distributing the 27 at the same time. Over 4n. This will look a little bit better because I'm just doing minus 18n plus 18 over 2. Okay. Don't have room to close my brackets. Act like I did. We could distribute the 3. Might as well. Let's distribute this 3 over n. We are just a couple steps away from being done, even if it doesn't feel like it. 3 over n. I'm distributing it, so let's get rid of it. So I'm distributing to here and to here. So that 3 has to go play with everybody on top. So 27 times 3, I think it's 81 n squared. Oh, 54. Oh my goodness. 54 times 3. It's not going to matter. You'll see why. It's going to go to 0. 54 times 3. 162. So positive 162 n plus, oh, there's that 81 again. All over, hey, denominator times denominator right here, 4n squared. Whew, 18 times 3. Well, that's 18 times 3 is 36, 54, I think. So I get 54n plus 54. And then, again, I'm doing denominator times denominator, 2 times n. And remember my rule on this. Whenever n is approaching infinity, I divide by the highest power that is in the denominator. So the highest power in this first one right here is n squared. So I divide everything by n squared. Well, 81 divided by n squared, when n goes to infinity, is going to go to 0. Same with him. So what I'm left with in this first one is 81 over 4. I've got the minus sign. Now, limit of the difference is the difference of the limits. So I'm also taking the limit of this guy, and I'm going to do the same thing. I'm going to divide by the highest power that is in my denominator. So 54 divided by something insanely large just goes to 0. 54 divided by a million is close to 0. 54 divided by a trillion is close to 0. And I'm left with 54 over 2. If I do this little thing in my calculator, we're just going to decimal it out. I get negative 6.75. That is the actual area underneath the curve x cubed minus 6x. If I was to draw this again, it looks something like that. The actual area, if I add this part and then subtract all of this, it gives me negative 6.75. All this Riemann sum, way back whenever we did this, 30 minutes ago it feels like, all this Riemann sum tells me is the approximate area. I didn't even get that close with it. Negative 3.9 and the actual Riemann sum was negative 6.7. So anyway, that would be my actual answer. We made a mess of my board again. If you're looking for a spot to pause and collect yourself, I am about halfway done with this. So you can tell this is going to be a large video. I would hit pause on this. You can go to the end, check the homework, and see what's happening as far as some of the problems I ask like this. Obviously, some of these will be tedious and long whenever you work through them. You need to practice on them, okay? And luckily for you guys will have ample time to practice this. So this next example I'm about to do would actually start what would be day 2. I need to erase all that. Such good work. To set up an expression for this as a limit of sums. So this is just wanting me to work it backwards. I want to work on setting up that limit again, just like we just did on that last example, part B, because I think that can be the trickiest part. And if you can't even get started right on the problem, it's gonna be tough getting it to the end, obviously. Okay, so I'm gonna go ahead and set it up. I got delta x equals b minus a. In this case, it's going to be 3 minus 1 over n. So, 3 minus 1. This is my 5th video I've made today, so I do reserve the right to make a 3 minus 1 mistake like that. It's going to be 2 over n. Okay? Now, this time, my first subinterval starts at 1. And as I go to the next one, it's going to be 1 plus delta x. Well, unfortunately, this time, it does not simplify any, okay? Whenever I start at 0 and I go to 1, unfortunately, what happens is I'm starting at 1 right here. I add 2 over n. This guy has to be 1 plus 2 over n. I don't have any way to simplify that since they're not like terms. So you can see where this one will be a little bit messier. So I have 1 plus. If I add another delta x to this, if I add another 2 over n, now I have 4 over n. I think you kind of see the pattern where I'm going to this. If I add another delta x to it, I have 6 over n. If I add another delta x to it, I have 8 over n. Once you can get that pattern down and you can get this x sub I, you're in good shape. Because I always started with 1, and then I took whatever this subscript was, and I multiplied it by 2. So that's going to be 2i over n. It's a little bit messier to work with this time, but I should be able to go forward with it now. We're not going to actually find this area, just because you have an example like the last one. This one will work very similar to it. Okay? So remember, this integral right here, it's taking the place as the limit as n goes to infinity of the sum as I goes from 1 to n. Okay? And I've already worked in the 1 and the 3 over here. And so all I need now is my f of x sub I times delta x. Well, f of x sub I is just going to be my f of this guy, 1 plus 2i over n. And then my delta x, we said was 2 over n. Okay. So what I'm going to do is I'm going to rewrite everything. I'm going to bring my limit down. My delta x, you can leave it back here. It's not going to bother me, and it won't be wrong. But I'm going to move it up here in front of my sigma. I just want to get used to doing that. And I need to take this 1 plus 2i over n and I plug all that in to this x. E to the 1 plus 2I over n. And this is what it would be looking for on there. Okay? So you'll get some practice just rewriting this. Okay? And hopefully that'll step you up into a problem like we just did. Whew, man. Well, no more long problems. Not that that one was long, but the one before it, I'm still trying to collect myself after that one. But I want to really get into the idea of you knowing what an integral does. I didn't know this when I was well into calculus. One of my buddies, his name was Sean, he said, "Why are you taking an integral?" I said, "I don't know. I could find an integral. I could work all this math. I had no idea what I was doing." But this example will kind of remind you as to what you are working. Okay? And so it says evaluate by interpreting each in terms of areas. Whenever you see this, we are going straight geometry on this. Okay? We're not, drag down. I want to. Yeah, straight geometry on this. So I want you to think back to your geometry days. And so what we're looking at on this, if I was to actually just set this equal to y, I could square both sides. And I get 1 minus x squared. I could add x squared to both sides. And I get x squared plus y squared equals 1. Back in pre-cal, we said that was a circle. We said it was a circle centered at 0 with a radius of 1. Well, if I'm just wanting to go from 0 to 1, I'm just wanting to go from here to here. And remember that this square root can't take on any negative values, so I am just wanting the area underneath this curve right there. And so to evaluate this, this is just going to be, let me rewrite the original problem. The square root of 1 minus x squared dx is simply just going to be the area of a circle. The area of this circle is going to be pi r squared, where r is equal to 1. But I don't have the whole circle. I only have a quarter of it. So I'm going to multiply it by 1/4. And so I can actually evaluate that to just simply be pi over 4. And that would be the area underneath that curve. That one's kind of weird. That one's kind of hard. All right, we're getting the circle out of it. Let's do one that's a little bit more basic. All right? If I have y equals x minus 1, I know good and well that that is a line with a slope of 1 that, sorry, I'm trying to talk and write at the same time, that goes through the y-axis at -1. And I'm wanting to evaluate this again from 0 to 3. So I'm wanting to find the area underneath the curve from 0 all the way to 3. So I have all this right here. And I have this little region down here. Now you have to kind of think back to what we talked about in the first half of this video. Whenever I'm looking to find this, I have two different areas. I'm going to have a red area, and I'm going to have a blue area. And that blue area is down underneath the curve. Okay? But they both form triangles. So let's do the red area first. Okay? So that red area is going to be, well, if it's a triangle, I'm using 1/2 base times height, which will be 1/2. Let's see, my base is 2 units. And then my height, it came up 2 units as well. So that gives me 2. Now let's look at the blue area. The blue area is still a triangle, so I'm still going to use the 1/2 base times height. And I have my base is 1, my height is 1. Either way I wanted to do it, I get 1/2 times 1 times 1. So the area of that blue triangle is just going to be 1/2. But here's the kicker we have to remember. It's that if something is below the axis, we have to subtract their areas. And so I get 2 minus 1/2, which will just give me 1.5. And so if I was to evaluate this integral, it would be 1.5. In the coming weeks, we will learn a better way to do this where we're not relying on a page-long problem and we're not relying on geometry to find this. And it will work for any curve that we want to do. These just happen to work this way because whenever I graph them, I get the nice geometric figures of a circle and I get triangles. And so there will be some of those. Keywords to look for that on that, though, is each in terms of areas. Okay. Now, the other day we talked about the midpoint rule. The midpoint rule, okay? So whenever I'm doing the midpoint rule, what I want to do is I'm still going to do, I think I'm missing a limit on here. I'm still going to do the sum as I goes from 1 to n. But this time, whenever I'm doing the midpoint, I'm going to do it of x bar, okay? X bar just means average, or it means the mean. It means it's going to be halfway between the left endpoint and the right endpoint, like it was on the last video. Okay? And of course, I'll multiply that by delta x. And I'll add that to the midpoint of my second subinterval times my delta x. All right? And I just keep going with this until I get all the way to the last subinterval. I'm going to do the midpoint, halfway between the left and the right endpoints of my delta x. A lot of mathematicians say that this is going to give you a better idea as to what the actual area could be. Okay? And so here's my formulas for everything else. My delta x hasn't changed, and this is just a formula for finding the average. We're just going to find the average, what's halfway between two numbers like we've done before. Okay? So let's get a function. The function is going to be 1 over x. It's going to be a Riemann sum. So I'm just going to use 5 subintervals from 1 to 2. Okay? Let me draw a picture as to what's going on. 1 over x, remember, is this crazy looking reciprocal function that has 2 branches that form a hyperbola. And I'm just wanting to go from 1 to 2. I'm wanting to find the area underneath the curve from here. So it's a little bitty area right here. And what I have to do is I have to take this area and I'm going to divide it up into 5 subintervals. If I divide up from 1 to 2 with 5 subintervals, we have a formula for that where I just do b minus a over n, 1/5. That tells me that each subinterval from 1 to 2 is only going to be 1/5 units long. So 1 plus 1/5 is 6/5, 7/5, 8/5. I didn't probably squeeze that in. 9/5. Those are going to be the endpoints of my subinterval. And what I want to do is I want to go in between. Messed up, of course. So I'm going to change all of these to decimals real quick. 1, 1.2, 1.4, 1.6, 1.8, and 2. It's just easier to do with decimals. So all of these red numbers came down and landed as these decimals. And whenever I do the midpoint on this, I am just going halfway between 1 and 1.2, 1.1. Halfway between 1.2 and 1.4, 1.3, 1.5, 1.7, 1.9. I can keep going up like so. I'm ready. All right. I'm just doing n equals 5, so I really don't need the whole integral right here. Instead, I'm going to take the limit. I'm not even going to do a limit. I'm sorry, because I have 5 subintervals. I'm going to do the sum as I goes from 1 to n, which in this case is going to be 5. I have 5 subintervals, and I want to do length times width of each one. Well, they all have a width, we already said, of 1/5. So, 1 over x dx. It looks kind of weird writing it like that. I'm going to go with it, though. So I'm going to go ahead and pull my dx out in front, so that way all I have to do is plug in each of these midpoints in for x. It's kind of nice this time because I don't have 2 different ones to plug in. I think you see the pattern with this. 1 over 1.7, 1 over 1.9. And it just turns into a calculator file. I'm not expecting the answer to be very big. Look how small that number is. And so I get 0.691908 when I type all that in. We like Riemann. We like it when we have n equals 5. And you'll have it both ways on your upcoming quiz. Hey, 1/5. Let's look at some properties of definite integrals. And that's going to make it so hopefully when we come back after this coronavirus outbreak, we'll be able to just zip through problems pretty quick because we'll have these down. If not, we can go over them again and talk about them. But we'll also be using some. Some of them we've already talked about, okay? So the first one I want to talk about is the integral from b to a. Oh, they wrote that backwards, didn't they? We're used to seeing a to b because a is normally smaller. So if they mess up and write it backwards like that, I can definitely just turn it around and do a to b and then throw a negative out in front. That won't happen very often, but I'm just going over all of them, okay? Now, again, let's draw out what this means. I'm just going to make up a random f of x right here. Suppose I want to find the area underneath this curve from A to A. That has no width. 0 times anything, something with 0 width times the height is going to be 0. Okay? And then if I have the constant, if I'm taking the integral of a constant, it's going to be c times b minus a. That'll make more sense later. Just getting these out of the way. And then I can also distribute the integral through, oops, let me put the dx. The constant can come out in front, just like the sum. It's like I'm reviewing all the sum ones from the beginning of my talk, which was like 3 days ago, it feels like now. But the constant can come out in front. And of course, if you have subtraction right here, it's going to work the same as addition. I can do the sum of a to b of f of x minus the sum of a to b of g of x. I always forget my dx, so in dx is right here. Okay. These are all proven in your book. If you're having trouble believing me on some of them, they get into limits and they follow the limit laws. Since I can do this with limits, I can do this with integrals. And so that's how it kind of works. Okay? So we're getting into our last steps before we're going to be able to do this a little bit quicker. I hope. Man, I've been racing too much today. It's not working. So I'm going to use the properties of integrals to evaluate this. Okay? So first thing I see on this integral is I can take the integral of each side of this plus. All right. The next thing I see over here, I'm kind of done with this side for now, so it's just going to come down. But this 3, anything that's multiplying my x can come out in front of the integral. I'm about to do some magic. Okay, so property 1 on the last slide says if I'm taking the integral of a constant, then I just have to do the constant times the difference of the endpoints. You just have to trust me on that for now. Have that written down somewhere in your notes. I will be able to prove that a lot easier come next week. And then this guy looks familiar. Yeah, we talked about that. We actually did that back in 5.1. We found the area under the curve from 0 to 1 of x squared. We said that that was simply equal to 1/3. So this gives me 4. This gives me 1. My answer would be 5. Last page of the notes, guys. All right, property 5. Suppose I have the same function right here. Let's draw this out, have it make sense to us. Suppose I have the same function right there, f of x, And I have one guy going from A to C, and then the same function I have going from, man, that graph is crooked above. Going from C to B, from C to B. If that's true, and you can use this middle point, C is the same both here and here, then what I can do is I can just simply write this as one continuous integral from A to B. How does that help? Not just a whole lot, but we will use it. Let's actually use it right now. Okay, I'm not even given a function on this one, but let's draw it out. Let's just suppose I have this function f of x, and I got to go all the way to 0. I know from 0 to 8 right here that the area underneath this curve is 12. And I know from 8 to 10, this is not different. I don't know what that is. But I know that the area underneath the whole thing right here is 17. This is as easy as it looks. This question mark right here has to be 5. And so the area from 8 to 10 underneath this function, b of x, is equal to just 5. So draw a picture on these if that helps. Last up, we have the comparison properties. Comparison property says that if f of x is greater than or equal to 0 for x between a and b, then the area under the curve, or the integral from a to b of the function, has to be greater than or equal to 0. That's kind of a no-duh thing. It's saying that, if you take a function and it's always above, it's always positive, it's always above the x-axis right here, then if I find the area underneath this curve, it's got to be positive as well. That's kind of a no-duh thing right there. Now, f of x is greater than g of x. They're kind of building on each other as we go down. If this is true, then the area underneath the curve for f of x, or the integral of f of x, is greater than or equal to the area underneath the curve of g of x. Let's just build on our pictures over here, okay? Suppose that I draw a new f of x, and I let this red line be my g of x. Again, this is a no-duh thing right here, that the area underneath this blue line right here is going to be more than the area underneath this red line. Suppose this area came out to be 1. I could easily see that this area underneath the blue line would come out to be 2. It's always got to be bigger because there's more area underneath there. So that sets up the property that we're going to use the most in here, this property 8 right here. It says if you have a min m and a max capital M for all x between a and b, then the minimum times b minus a is going to be less than or equal to the integral from a to b of f of x dx, which will be less than or equal to the maximum times b minus a. Again, I want to do a picture on this, and then we'll work an example with it. So it's saying that if you have a function, I'm going to let my function be f of x right here, and I was to pick a value right here that this function always stays less than, and I was to pick a value down here, I'm going to call it a minimum, that this function always stays greater than. It's saying that if you were to go from a to b underneath this function, that this area is going to be smaller than this area, and that's going to be smaller than the area that's underneath the maximum line. It's almost like a sandwich theorem that we've done before. Okay? So let's plug some numbers in and see how we're going to see this in the homework. Okay? So I want to use property 8, that last one I circled. Ooh, let's not erase it. Let's just leave it up there. Here we go. Let's use property 8 to show this. Okay. Now, first off, I need to go ahead and establish my max. All right, I can go ahead and establish my f of x too. I think we got that. Okay, but I need to go ahead and establish my max. And whenever I graph this exponential function, remember exponential functions normally look like this. They look like a slide going up. And if I reflect it, it's just going to be a slide that comes down the other way. So I definitely have a decreasing function on here. So the highest point on this graph between 0 and 1 right here is going to be at 0. Okay, so let's go ahead and find out where that is. E to the negative 0 squared. That's just 0 squared. Negative 0 is still 0. The max is going to be 1. Okay, so I can come down here and plug in 1 right there. Now the minimum value, since this thing is decreasing the whole time, the minimum value is going to happen right here. All right, whatever that is. But the minimum happens at 1. So using the same math that I just did, if I plug in 1 in for x, it will tell me where that dotted line is, that minimum that I'm always greater than. All right, so 1 squared is 1. I got e to the negative 1. I'm just going to write it as e to the negative 1. And that comes down here and gets plugged into my minimum. My b and my a are my limits of integration, 1 minus 0. I'm not looking to touch this guy. I'm actually trying to estimate him. And I got b minus a on this side. It's going to be 1 minus 0. Well, 1 times anything is itself. And this is all I can get from it. If you want to tell me what e to the negative 1 is, I think it's 0.367. So I expect whatever this integral is right here to be camped between 0.367 and positive 1. That's a lot of words. I hope you spend a couple days, maybe even, I'm even going to give you 3 days to work through this if you need to. Work a little bit of homework each day. And anything from these notes or the homework that you don't understand, we can go over it in the Q&A later this week.